heard the name being mentioned in the keynote as well. And MYOB actually has one of the largest SQL database implementations in the world. So it's pretty big. And between the both of us, I think we've got a bit of experience with both cloud as well as in architecture. Now, before we actually got, when we first decided to talk to TechEd and so on, we said, we've got to write an application that showcases some of the patterns that we're actually talking about. And every time we actually spoke about it and said, what kind of application can we write, kind of like ended up with some kind of a social theme in it, like a Facebook app or a Twitter app and so on. And so we said, what? We're going to write an application that kind of like a Twitter clone, that mimics Twitter. And he said, we got to make it even better than Twitter, slightly at least. By the way, how many characters does Twitter take? Anyone? 140? Well, we just make it 150, right?
More is better.
Straight away.
More.
All right.
Better.
And of course, we didn't want it to do exactly what Twitter did. We wanted to, do something else. We wanted to hit a niche market. And we said, hey, John, what do you like to do a lot? He likes to whinge a lot, right? As it turns out. As it turns out, a lot of people like to whinge. So there's a niche market for us. We're going to write an application that will allow people to just whinge. And we decided to call it Whinge Pool. We kind of have this inspiration from Whirlpool. This is where the forum where people go to whinge with their right? So we decided to call it Whinge Pool. And so we're going to have a quick demo of the Whinge Pool application itself.
Yeah, let me switch over. There you go. We couldn't get like the AKA URL yet, but it's actually live. You can go ahead and whinge about anything other than this talk. Right? Do not whinge about the speakers. They do not frighten the children, right? But it's a simple little application. It's simple. It's federated to Twitter. You can log in. You don't have to do anything. Just it goes off to Twitter and sends you back and all this lot. And it's a pretty simple little application. Now, if you think about it, from a cloud perspective, an application of this kind, the guts are actually the logic behind it. And you need to worry about all of the things that we're going to be talking about in terms of being able to scale, in terms of being able to stay alive, provide a service, actually make sure that you don't fall over just when the load changes. You've got to be able to handle all of that. So come on, don't worry about it.
Keep going.
Yeah. Right. Right. So the idea is that it's actually an interesting application. So it's a demonstrative application to try and address the issues that we're going to talk about and have a bit of fun along the way. So go ahead and whinge if you like. We'll come back to how this stuff is built, and then we'll talk about the patterns that we kind of addressed, the concepts that we use. And then finally, at the end of it, we'll come back and look at how we actually put this whole thing together and utilize those patterns.
Yeah. Thanks, John. If you have a Twitter ID now, you can just go into that website over there, which is whingepool.azurewebsites.net. And, mobile phone, laptop, tablet, whatever, just go in and you can actually whinge if you like.
I'll switch back to you. 2, 7.
And we'll come back at the end of the talk and see how many people are actually whinged. Okay. So just quickly recap on a few things. And first and foremost, we want to see what do we actually, if we are using some kind of conventional design and things like that, how using the things that we know today, how do we actually build this, right? First and foremost, what people actually do is we use some kind of layered approach, and kind of use some kind of presentation layer, business layer, domain layer on, and then we have some kind of a dial layer. We have some cross-cutting concerns like security on the side, and that actually talks to the database. This is actually a great way of doing things, right? You kind of a nice way of introducing decoupling. You can start independently changing some of these layers without affecting some of the other layers. As long as the interfaces between those two are, the same. How many people actually use this kind of architecture, right? Pretty much everyone. Every hand should go up. Right? We all use this, and this is great. One of the things is this actually always works. The other thing that people actually do is, we use some familiar tools and patterns all the time. If you're writing a web application, you go and say, you know what, I'm going to use an ASP.NET web forms or MVC app. And we also, if you want to expose some kind of an API, we use web services. Pretty much a lot of people still use WCF, expose things in WSTAR protocols and things like that. And of course, we all tie it down to some kind of relational database, most of the time SQL Server. Right? How many people kind of like follow this pattern? Again, pretty much like everyone, right? We all do this. And when it comes to deployment, we all do something like that. We have some kind of a load balancer, and we have a whole bunch of web servers connected to the load balancer. The load balancer can be, I don't know, like a hardware load balancer or software load balancer, doesn't really matter. And then when we talk to the database, we use some kind of a clustering, like an active passive clustering. And if one of these servers actually fails, and then it switches over to the to the other server, and the database itself resides in some kind of a SAN, typically. Again, like how many people use it? The last time I did this talk, and I said like pretty much everyone, stock standard. This is what we actually use. It all works. You kind of like have availability because of you've got load balances in multiple, in a web farm, you've got multiple servers over there. Again, you've got kind of availability over here. If one of the servers actually fails, you can actually switch over to your other server. And two things that actually show, that I would like to say over here is like, if you, ask the room how many people use it, everybody puts their hands up. So first thing is, these are familiar things that people have been using, A, right? And B, we're using this mainly because it actually works. So I'm not here to bag any of the existing patterns or any of that stuff, right? All the stuff actually works. And if I were to, write some project, I may use some of these things today as well. But when you want to actually start writing cloud scale applications, right? We actually said earlier something like a Twitter clone or something like that. Twitter takes something about 4,000 tweets a second. Actually, think about it, 4,000 tweets a second. So by the time, from the time I actually started this talk, or we were mucking around with all the display things and so on, there have been millions and millions of tweets that have actually happened. That's pretty big. So is there a better way of, when we have that kind of a scale, can we do things in a slightly different way? And that's what I want to talk about. So, if cloud application, how do you actually start thinking about scale? So first thing I want to lay out or get out of the way is the definition of cloud itself. My definition of the cloud is, it's basically computing processing power or resources such as storage shared across the internet. And it's available as a service. That's my simplistic definition of the whole thing. The reason why we actually moved to it is one of the main reasons is that basically there's zero upfront cost in setting it up. If you've got a credit card today, you can just go over to Windows Azure and then create an account, and straight away you can have your services up and running. And there's also very low operating cost. So your ongoing cost, sometimes it's actually charged by the minute. So I think if you set up a VM on Azure right now, it costs about, like an extra small instance, costs something like 4 cents an hour. And if you're running it for 15 minutes, it's costing you like 1 cent. I mean, how can you actually compete with this kind of cost, right? And of course, cost is not always the main thing. It's this whole concept of elasticity on demand. So if you wanted more service, you can just get it just like that. You hit a button, or you move a slider, or you make a REST API call, and suddenly you've got a new server provision. I mean, I worked in like large enterprises, and if you want an extra server, you got to fill out forms. I'm talking physical forms where you need signatures and things like that. And 3 months later, your server is still not provisioned. The cloud does away with all of that stuff. You got this elasticity on demand. Effectively, it's a seemingly infinite, inexpensive computing power at your disposal, right? That's the main advantage of it. And so, how do you actually architect or design applications for something like that? John?
Sure. So one of the reasons, it's a good point, right? One of the reasons why the cloud is so cheap and elastic and all of that is because they basically commoditized the business of getting you these resources, right? So you have cheap hardware, plenty of commodity hardware that's been just put together it doesn't, you're potentially sharing it with a whole bunch of other people, so it's multi-tenanted. All of the cost of managing this stuff, you're not paying for it. You're paying for it amortized, all of that stuff. It just turns out that you don't really need to do that every time. And if the requirement of maintaining referential integrity turns out to become a hindrance, then you really start wanting to look at a different way of storing the data. So when you run into a whole bunch of other situations where you don't really need the referential integrity, but it starts getting in your way and slowing things down, that's when you want to look at the NoSQL databases as your data stores. So let's go back to CQRS side, right? We started with the idea of having this command. It was going to go through some fairly chunky workflow type or fairly chunky business logic type processing. And you don't want to actually, and then you think about it, that's the thing that's going to take a lot of time. So every request that comes in, you're spending time waiting for that request to get completed. And that's going to reduce your scalability. So one of the things that you want to do, how do you increase the scalability of handling those commands in the first place? So let's go with, let's take a look at that diagram first. What if I took those commands and instead of processing them instantly, stuck them in a queue? What does that give me? Well, for starters, I become eventually consistent, as Mahesh pointed out. I just add a little bit of lag to the system, right? But I also get the ability to now have 15 people looking at that queue, or 23, or 280, depending on the load, how big that queue is. By monitoring the size of that queue, I can actually scale my application, right, to handle each of those commands. And the command might require, the processing of the command will obviously change something in the database. But by using this kind of a mechanism, I have now just introduced the ability to scale horizontally on the processing side. So while I'm able to now deliver the data quickly using the appropriate data store, I'm now also able to process more information, process more commands in a scalable manner. And that's the motivation behind using this queue-centric workflow, right? So let's go back to the concepts behind it. Alarm bells probably going off in your head thinking, you can't possibly do that. What if there are dependencies? What if I change something and that has an effect on something else that happens? And all of those are true. All of those constraints are true. You can't do this all the time, or you can't do it without managing other stuff all the time. But if the principle is simply to isolate units of work, make sure that the isolation follows certain characteristics, which we'll talk about in a minute, and then you get yourself the ability to scale out. That's the general concept. Now, what are those concepts, right? The concepts are, you've got to make sure that each piece of work is as close to being atomic as possible, right? And if there are dependencies now that start acting, if there's a state machine or something that you need to build, you build that over and above this to manage that. The reason why is because the system that you're talking about has to still be resilient. So you can imagine a situation where you enqueue a command, or you enqueue 5,000 commands onto this queue, and you're processing happily along using 3 or 4 workers, and worker number 3 stumbles upon a command, and the machine that it's running on dies. That's life. That's what the cloud is. You've got to design for that, right? Now, what happens in that situation? Do you just ignore 3 and move on, or do you do something else? It turns out that with Azure queues, there's a property that removes a whole bunch of edge cases. It's called a guaranteed once processing. That concept ensures that, okay, it says the implementation is pretty simple. You dequeue something from the queue. The queue sort of tells everybody, okay, I'm not going to tell anyone about this item for the next 15 seconds or whatever it is. If in the next 15 seconds you do not delete the item from the queue, thereby signaling to the queue that you have finished with it, it says, okay, the guy that took this is no longer around. I'm going to put him back on. Now, in a situation like that, you may have finished half the processing on it. So the key idea is you want to keep the processing units really small, and you then introduce this concept of idempotency. When you write the command, it's no longer just a question of add 5 to something. No. You've got to make sure that if you play the same command twice, it has exactly the same effect. And that's where the complexity in writing your code starts becoming evident. Because you now have to craft yourself into this mindset of thinking, okay, if this thing dies here and then starts up again, how do I make sure that I don't debit this guy's account for $5 million twice? Right? You got to make sure that you play these things as idempotent operations. You want to make them atomic, you want to make them idempotent. And I'll talk about the poison messaging handling, because when you build systems that deal with this, the failure may not necessarily be the infrastructure failure. The failure may be a bug in your code. I mean, heaven forbid that we all write bugs in our code, right? But they happen, they're life. So now you have to deal with
Michael John.
Not in his code. I figured out how he doesn't have any bugs in his code. He writes all his code in Visio.
Thank you.
Right. That's not true. But if there's a bug in your code and you find a message that you choke on and you bring the worker role down, the queue will make sure that the message comes back in there. As you'll make sure that the instance comes back up and your worker is able to pick up the item again, you may be a little bit out of sequence in the processing of the message, but you will hit that message again. And you will choke again. And you will die again. Now, it's very conceivable to think of 4 workers sitting there pulling things off the queue, and they all choke. Eventually, they'll find 4 poison messages, and all they're doing is choking on the poison message, putting it back on the queue, coming back up, choking on the next poison message, and you can pretty much grind yourself into a halt. So this is a very practical tip. You got to make sure that you keep an eye on the number of times a message comes back in the queue, and as your queues support that natively. So that's an excellent piece of information that you need. You need to kind of like take care of that. So if you find yourself spinning on the same message, 15 times, it's unlikely that the infrastructure died 15 times. It's more likely that the bug's in a code and you've done something stupid. So, put that in a dead letter queue or do something with it and then move on. The other thing is when you have apps like ours, right? Built for scale, 6 whinges so far, right? I wish people would whinge more. That's my whinge, right? 6 messages. So what's the thing doing? It's sitting there, furiously polling the queue, saying, hey, do you have any work for me? Do you have any work for me? And now I've got 4 workers doing that. And guess what? Microsoft charges me every time I do that. So if I don't have some kind of intelligent exponential backoff, Microsoft has a direct line to my bank account at that point, because I'm leaking money left, right, and center, right? So you want to be aware of a couple of these considerations. But the key things, the ones that make it kind of difficult, this is the curveball part, right? Make sure that the piece of work that you're working on is not generally just an update. It's an ensure. Like an insert is not just an insert. An insert first checks to see if it needs to insert, or if part of it has already been inserted. So it's more like an insert or replace or something along those lines. Semantically, you've got to be thinking about idempotent ways of operating, or making sure that, if you see an old version of this, because you've got some correlation ID associated with a piece of data, that you remove what's there and then replay it. Make sure that stuff is idempotent. And it's much easier to make it idempotent if it's small, so make sure that it's consistent within a single transaction. So how have we done it? We've done exactly that. We use Azure queues, we dequeue, we process and then delete, and then we don't care, because we're guaranteed that we'll do this. We just keep an eye on the number of times we see a message, deal with all of that stuff, and then we do something slightly more intelligent. The way in which you handle a command is actually quite interesting, right? Should the queue know anything about the commands? I don't think so. The command handler that pulls the thing off the queue, should it know anything about commands? Actually, it doesn't have to. If you crafted your commands so that they were self-describing and say, I am this command, I'm handled by this kind of command handler, you can have a quite generic queue processor that pulls a command off, interrogates the command and says, hey, what are you, who's your handler? And then looks to see if the handler is available. If the handler is available, it gives the handler the job and says, please handle this message for me. If the handler isn't available, you can download the handler from blob storage or some other mechanism of dynamically adding functionality. So now we actually have done this. We've done this in a way that now allows us to create commands that we didn't know of when we wrote the software. Months later, add a new type of command, upload a new command handler to blob storage, and I have new functionality. And I didn't even have to slow the system down once to do it. Upgrading the system, making it future-proof, is native behavior in a cloud application. If you don't do that, you're going to be in a world of pain, because you're going to have to deploy bug fixes at 2 o'clock in the morning, and hopefully you're at the end of some kind of CI pipeline where you've tested something and you want to do continuous integration and you want to deliver stuff as soon as you finish developing it. You don't want to be bringing production systems down. You want to be able to check in something, run the tests, pass the feature, push out a new command handler, and you have new functionality. It should be that way. And this kind of architecture actually allows you to do that. Where are we now? Right. Okay, let me, the other thing about queues, right? And I'll hand it over to Mahesh in a minute. But the thing about queues is that as your queues guarantee that your message is going to be processed once, at least, right? So at least once, they'll guarantee it. Problem is, anyone who's done anything with queues, what's the first property? First in, first out, and then you forget about it. You get to process the thing exactly once, right? I mean, at most once. So it's at least once, and then at most once. You never get to see the same command again. Now, wouldn't it be useful to remember that you've actually processed a command somewhere and then be able to derive some secondary benefit from it in the future? Sounds like a good idea to me, right? If I'm saving a bunch of stuff, we do that with audit logs and audit trails and stuff like that. We could do the same kind of thing, but at the business level, and keep storing those commands have been executed type events into some kind of store, right? Like an event source.
Yeah.
There you go.
Thanks for the segue, John. A long segue.
A long segue.
So, forget all this complex thing that John actually said, right? I want to explain even something, using an example. I think it's a lot more easier to actually to visualize it. And so we'll go with the old way. Typical example, you got a shopping cart. You want to go buy a book. You go into a website, add a few books, and you check out. So let's see how it's actually done in the old way, right? You kind of like have some kind of you store the data in the database. Basically, all you're doing is storing state, right? So the first thing is you want to go and create a shopping cart. It goes and adds an item into the cart table, if you want to call it that shopping cart table or whatever. And of course, you've got another table called cart items that actually stores a bunch of the items that you've actually added. You go and introducing .NET 4.5 book, and sure enough, a new item gets added over here. You add another book, again, another one gets added over there. But you say, hey, you know what? I don't want that book. It's too expensive, whatever. I'm going to get rid of it. You go ahead and remove that book. That gets deleted from the cart items. Pretty simple logic. This is what we all do. And then you add another book. Another entry gets added over here, and you finally check out. A whole bunch of other things happens, right? It takes a credit card number or whatever it is, and then you finally check out. This is one way of doing it. If the application actually crashes at, maybe at this point, as an example, right? Or, your web server actually crashes. Your traffic gets diverted to another server. All it does is look up that table. I use table very loosely. It could be just something in memory, right? It could be in your session state or whatever even, right? All you do is basically load that whole thing up, and you continue on. Now, what if we actually did this in a slightly different way? What if we actually said, you know what I'm going to do is I'm going to store all these as things that have actually happened in the past, a bunch of events. So as soon as I create a shopping cart, it says, hey, well, the shopping cart has been added, and you pass in a bunch, you store a bunch of data associated with that, creating the shopping cart. And you go and add this book. Well, book has been added. You go and add another book. Again, it actually says another book has been added, and you pass the data of the book too. And then you actually remove it. Now, interesting thing over here is you actually don't go ahead and remove that entry that you just made. Instead, what you actually do is you add another entry that actually says, hey, book 2 has now been removed. And finally, you go add another book, and then you check out. So you notice that all we're doing is storing a sequence of events that have actually happened, and the data associated with each and every event. And if, for some reason, the application actually crashed that point, all you need to do is play those events back, and it restores the state of the application, right, to where you want it to be. That's pretty much what event sourcing is all about, right? It's a way of persisting application state, but instead of actually storing the current state, we actually store it as a history of events. So what is an event? It means something that's happened in the past, and it's got a whole bunch of related information about the event itself. And another good example is, like a chessboard. If you think about the chessboard, what you can actually do is you can look at the chessboard and say, well, I'm going to store exactly the position of each and every piece in the board. I'm going to store it in the database. And if you want to retrieve that, all you need to do is go ahead and retrieve that. And that's one way of doing it, and it works fine, yeah. But what if you actually wanted to look back and say, hey, how did I actually get to that point? Right? If you had actually stored the history of each and every move, you'd be able to play back all those events and then get back and see, okay, now I know what it is. So there's a lot of useful information in there that you can actually use. And I know, people are saying, well, chessboard, storing all the events, that's like a trivial, like a app. What about like enterprise-side, applications and so on and so forth? How about things like an accounting package? It turns out this man over here knows a few things about accounting packages. And if you ask him, he'll actually tell you that it's actually a great way of storing information, even for things like an accounting package. Every payment that's actually made and every payment you actually receive, you actually store it as a series of events. And you look at you look at what your current balance is, you can actually derive that quite easily. And what's more important is that history of events is equally important as the end state of the application. So how do you actually implement it? I mean, it's pretty straightforward. I mean, you can actually use a stable storage to store all your events, or you can actually use this you can you store it in SQL Server as well. Now, if you're probably twitching and you're thinking about, if I replay all the events to get back my application state, what happens when the application actually crashes? Yeah, no problem. All you need to do is replay those events. But you said it's cloud scale, right? What if there are millions of events? Are you going to play all those events? What's going to happen over there? So typically what you actually do is you actually take snapshots of the state of the application from time to time. So that if your application does crash at any point in time, all you do is restore the last snapshot, and then you'll play your events from that point in time. And of course, trust me, computers are pretty fast, and you can actually play back those events pretty quickly. But of course, you still need to take those snapshots. Now, event sourcing does provide a number of benefits to you. First and foremost, that application that were actually the example that I showed you about the shopping cart. Remember, the way when we actually stored just the state of the application itself, the fact that someone had actually gone ahead and removed book 2 was actually lost. But now we actually store that information. And you can actually use that information. We were talking about design for the future and things like that. You actually store that information. The next time this person actually signs in, you can start dangling with carrot and say, hey, this book is now available on special. Do you want this one? And you go like, yeah, you have all those kind of uses. There are many uses as well. You can use it for auditing purposes. You can actually see who's done what. All the audit purposes. And there's a bug in production, and you want to figure out how to do it. I don't know how we actually got to this state. But at event sourcing, you'd be able to play back those events and see exactly how you actually got to that state. Even if you wanted to fix something, right? somehow you introduce a bug in the code and it shouldn't have been processed that way, all you need to do is replay those events with the bug fix, and you can actually get, like a super calculation. There's something that went wrong, and we actually mucked up the calculation of super in code. Right? So if you're going to go fix it now, all you do is play those events with that bug fix, and it's fixed. Now, a couple of things that I want to point out. Typically, once you actually write an event to an event source, you don't go and modify it. Actually, as I showed you, you don't go delete it or you don't modify it. You actually put in a correction. If you remove that book, that's another event. Those are some of the things that you need to think about. So whenever you're actually dealing with things like event sourcing, you can actually imagine.
I've just got a question for you quickly.
Sure.
John, it's just it's fine to have your event sourcing, and you're basically going to get back to the state by replaying the events. But what happens if you had a bug somewhere, or not a bug, but a transaction that died? Something happened in the cube, the infrastructure failed. How would, I know you're talking about the IDO type of thing, ID, whatever it's called.
Fair enough.
How would you get back to that? And would you need to put in the kind of corresponding?
So it's
in your, when fixing it,
Yep.
to get it back up and running? Or how does that work?
So in an accounting world, that thing is called a contra entry, and you typically try to do that. In BizTalk, I think it's called a compensation. You basically apply the reverse function, and you try to do something. We can get back to that in a bit.
So before you play each one of those things, you'd have to check that it wasn't done previously, and then if you would find out what was wrong, then basically write in the counter or the...
Sure. So let's take that offline. It's a very interesting conversation because it's actually quite involved, and a lot of the factors that will define the kind of solution you need will be influenced by the kind of problem you're trying to solve specifically. The primary need, the primary benefit you get from event sourcing is getting that audit log to first inform you why the error took place in the first place, and then subsequently you can use the information to analyze the data more thoroughly in different ways without actually affecting the application state. So you have many ways of actually solving this problem. But let's come back to that.
Yeah, the key thing to remember here is that the event source actually contains a list of things that have actually happened. So it's not like, if you're about to do something that actually fails, that event hasn't happened. But as John pointed out, we'll actually take this offline and we'll talk about this at the end of the talk. But when you're talking about event sourcing itself, you can actually imagine the amount of data that is actually generated. Right? I mean, instead of, adding this book, taking that book out and so on and so forth, people making a lot of whinges, Mahesh whinged about this, John whinged about that, and so on and so forth. You kind of like end up getting heaps and massive amounts of data. And so how do you actually deal with this kind of data? I mean, we're kind of like talking about petabytes of data, and we're kind of like crossing the realms of what relational database can do in terms of, running a query on that and finding an, average or sum of those things, right? So there's a pattern called MapReduce, and this whole thing actually comes from a paper that Google actually published many years ago. And they talk about how they actually handle this kind of a problem. One of the key things, right, is this, when you have this large amounts of data, what you should really be doing is, rather than actually have a big machine crunching all of that for you, right, instead you actually divide up the data and run it parallelly across many nodes. And we have this thing called this embarrassingly parallel problem. So what you can actually do, what really happens is, for example, if you want to count the number of words in a line or something like that, you can actually do that parallelly. All you need to do is pass the line to a whole bunch of nodes and let them all compute that together, compute that separately. And so MapReduce is kind of like a set of, it's nothing more than a set of programming steps that you actually to do to actually run through this data. Now, interestingly enough, how many of you actually went to Martin Grinnell's talk yesterday? Any of you here? Okay, a few hands. Now, the interesting thing was we actually did this talk a while ago in a user group, and one of the examples that we actually cited was, oh, the election is on. What happens when, we want to start finding out how many people are actually tweeting about Labour and how many people are tweeting about the Liberals and the Greens and so on and so forth. And they showed exactly the same example. I was sitting there talking like, damn, you guys stole our thunder.
Well, to be fair, they had a decent implementation of it.
Yeah.
We were just going to talk about it.
We're just going to waffle about it, so yeah. So how do you, I spoke about a number of steps to actually handle it. It's pretty simple, right? The first step is to actually split and store the data. And once you store the data, you run the map function on it. And it kind of like does some kind of filtering on this data. Effectively, right? You run some process and say, hey, well, and an example is, the election data itself. You have a whole bunch of tweets, and you start looking at the tweets and say, hey, okay, well, this guy is Liberal, this guy is Labour, this guy is Green, this guy is Independent, and so on and so forth, right? So you can actually run this on all the tweets individually and decide that up. You kind of like figure that out. Once you actually do that, you kind of like have the shuffle operation where you go in and take all these results and you kind of like sort it all out. You say, well, all the Liberals are going together, all the Labours are going together. And finally, in the reduce step, what you actually do is you combine all of them together and then say, hey, okay, well, 45% are talking about the Liberals and 38% talking about the Labour and certain percentage are talking about the Greens and so on and so forth. That's pretty much how the whole thing works. Now, how do you actually implement it is you use something called HD Insight in Windows Azure. It's a flavor of Hadoop. Now, I said Google actually I spoke about Google talking about MapReduce and so on and so forth. They came up with this paper many years ago. Now, Apache has an implementation of MapReduce, and it's called Hadoop. And HD Insight is Hadoop's flavor that actually runs on Windows Azure. And all this data that I actually spoke about that you want to put in, you can either store it on HDFS or on blob storage. And what HD Insight will actually do is it'll actually process that. Now, Microsoft actually recommends that you actually put all this data up in blob storage, so that even if you delete some of those nodes, the data doesn't go away and things like that. You can actually use a number of languages to actually implement the MapReduce itself. A lot of people actually. Because a lot of the origins of Hadoop and so on is from the Java world. A lot of people still use Java for it, but you can actually use things like C# if you wanted to. That kind of like sums up some of the modern patterns that we've actually used. Now, I quickly want to jump in and talk about how it all hangs together. Maybe John, do you want to summarize everything together?
I'm conscious of the fact that we started a little late. We have 10 minutes, so I might sort of go through this, and we had originally about 15 minutes for questions. What we'll do is we'll take these questions offline. We'll try and finish up as quickly as possible on this one. We've kind of walked through most of this as we've been going through the talk. You have a typical web application with a put or a post to an Azure website. It's just that the website doesn't do what we originally expected it to do, which was to write to a database, right? We've been through that. What we do is we post a specific command to a command queue, and a quite generic open source command processor is available to pull that off and process it. And in fact, all we do is write the command handlers and stick it into blob storage to pull that stuff out. We can then take that, and it turns out that the saving of a command, saving of a winge, for example, that first message is actually a save winge. And it carries 3 pieces of information. It has the winge pool that you want to winge to, the person who did the whinging, and the winge itself, right? And what we want to do on the query side is we want to materialize on the left side of the page all the winges that I have made. So I need a winge by user kind of view. And then I have a winge by winge pool, which are those panels that you see at the bottom when you create a new winge pool. So those are the views that actually feed those. Now, what we've done is use table storage to materialize the data and put it in there. So the CQRS pattern is starting to come out, right? The command goes into a queue. the query is coming out from a materialized view in table storage, and we have almost no filtering at all, right? If the filtering is by user, which turns out to be the partition key, or by winch pool, which turns out to be the partition key, that's fast and cheap in table storage. The listing's fairly straightforward, and you basically do a select star to put stuff into the panels. Yeah. So it's a very thin read layer. The command handling actually takes place by creating more commands. So I take the save winch, and then enqueue as its process. I enqueue the creation of a new winch pool if I need it, because I might have to put up a new panel. And then a command to register a winch against a specific user, which inserts a row into this table, or against the winch pool, which inserts a row into that table. So I'm materializing the view on the fly. So you're eventually getting consistent. It'll be eventually consistent. Eventually, the processing of a command will register independently against the winch pool of the user. So you get the eventual consistency pattern sort of coming out of that one. The command handlers, well, we of course write totally bug-free code. So we only had to upload the command handler about 47 times, right? Right? Just 47, but it works now.
We think.
And the last one we put up was the extended functionality, because at the time when we originally wrote it, we didn't have the event store. But without bringing the application down, we simply put up a new command handler that said, when a new message has been received, also log the fact that it was processed into an event store, right? That functionality was introduced weeks after the original development was done, in a matter of some time. We put that up, and the next winch that got put in got stored in the event store. So we've added new functionality as we go along. We've got the patterns that we've talked about. There's the CQRS pattern. There's the queue-centric workflow pattern. There's the eventual consistency concept coming through, some materialized views, dynamic command handling, an event store. We'll talk to Martin after this talk and try and get MapReduce going, and then we'll be really done. But go on.
I just had a question, right? So if you've got like the eventual consistency happening, that causes a bit of disconnect with the UI. So how do you stop, like, for instance, the same command getting executed because the results haven't flowed through? Yeah.
No, the command's executed only once.
Yeah. But the UI won't say that, because the view form didn't materialize yet.
Right. So let me handle that. Let me wrap up this thing, and then we can come back to the questions, right? So in effect, this is sort of the app that we wrote, the patterns that we have.
In terms of pieces, right? That is all written in ASP.NET MVC. It uses Angular and things like that. Web API is basically simple REST front for making all the gets and puts, and of course that's actually deployed in Azure website, the actual web application itself. Now we've got the worker roles, cloud services that are actually deployed over there. And that is the queue is actually is basically a Windows queue from Azure storage. The command handlers are actually stored in blobs. This is again stored in a table storage. That is actually again a table storage. That's pretty much all the components that we actually use from
Pretty
Windows
simple,
Azure
really, if you think about it, but it works, and it scales quite nicely.
Yeah, and the code is actually available. I'll actually show you the link before we actually wrap up. And I got a bunch of references for you that you can actually look at. And that's basically the link where you can actually go and look at the code, source code for Winchpool itself. And there's the book that's been put out by the Patterns and Practices group. It actually talks a whole bunch of things around event sourcing and CQRs and things like that with respect to the cloud. It's worth a read, in my opinion. Greg Young does a lot of courses and talks on CQRs and event sourcing and all that kind of stuff. So I highly recommend looking at his blog, or if you had a chance to go through his course, you can do that as well. And yeah, don't forget to fill in the evals and all these customary slides that I need to show. And I'll probably open up the floor for questions now.
Yeah. So to answer your question, it's very similar to Twitter, right? You tweet, it takes some time for your tweet to show up, right? And the same concept. So it eventually gets showed up. In fact, we use SignalR to push the change out, and that's pretty much what happens. So it is eventually consistent, and there will be an instant in time where potentially the winge is materialized against the user or the winge pool, but not the other way around. Eventually, though, both of them will actually show up.
Like my own scenario could be like complexity that you were debiting money and that's not you'd have to manage that.
That's the whole item potency piece that.
Yeah. So that's where the whole item potency thing comes in. To make sure that if you fail sort of halfway in between, stuff doesn't go pear-shaped.
Anything else? Any other questions?
Any other questions?
Yep.
Was there an architectural decision behind writing handlers instead of picking one of the ESB products like you have bespoke anyway? So why didn't you run bespoke in the cloud to manage your handlers instead of writing custom code?
It's a good question. We just thought we'd have some fun.
Yeah, I think it's more or less like we should, showcasing some of the patterns that were actually and how you can actually use it. I'm sure you can actually skin the cat in more than one way, but yeah. Anyway,
It's not so much the showcase BizTalk. The pattern is the same. It's about how you do it. Sorry.
What do you use to develop that presentation?
Prezi.
PowerPoint? No, this is PowerPoint. That's Prezi.
That's all right. So the question is, was there an architectural decision?
No. It was. This is a concept. It's not just around some Microsoft technology or some tool specifically. The concept is generic. It's applicable to any platform. You could do this using anything you wanted. So we did that. It's a concept. We use patterns like this to implement pieces of functionality at MOIB. Yes.
So
It's not the core of the flagship product.
the slides will be up. So I've got two.
But
copies
we
of
have
the slides.
several
One is on
operational
Prezi and the other one is
things
on
that we
actual
do
PowerPoint.
using this
The
pattern.
PowerPoint slides will be available almost straight away, I think.
It works
Prezi
pretty
slides,
well,
I'll
actually.
probably put it up on the blog.
The
Search for my
queues can take about 10,000
should get it.
inserts a second. So, yeah, well, and then you can put as many workers as you want. So you have the ability to really scale out. Thank you. Thank you.